So now we're going to do area bounded by two or more curves, except that these are going to look a little bit different. So I want you to notice that on the conditions here, what we have is we have curves that are x equals and x equals. So what we're going to notice is these are not necessarily going to be functions. They are often just considered curves that don't pass the vertical line test, but we can still find the area in between them. So what I want you to notice is everything looks very, very similar here. We're still just adding up, an infinite number of rectangles, except that the width and the height of the rectangle are perpendicular to the ones that we were doing earlier. So what we have are, if you look at these pictures here, so we're trying to find the area between two things that look like this. So notice you have more of like a vertical aspect. And so what that means is our rectangles are going to be these like horizontal rectangles. And the key thing to see is that if the function on the right here is, for example, f of y, and the function on the left here is g of y, then the height of the rectangle, and again, I'm using these arbitrarily, but we'll say height is f of y minus g of y. Because it's simply the distance, those are x values, and that's the distance between those x values. And then the length of the rectangle, and again, I use these arbitrarily, is simply your change in y or your dy in this case. And so multiplying an infinite number of those together as the dy gets smaller, the change in y gets smaller, is going to allow you to find the area. And so then that's found like we saw on, actually, I'll do one of the next slides here, but the exact area then just becomes, if you are integrating from C to D, so notice this is a vertical limits of integration here, from C to D, then it's every single difference in those x values times that height of each rectangle. So that's the idea. So let's take a look at an example, and I think it'll make sense. So what I want you to notice with the two examples that, or the example that you see here and the other one we're going to do is, the first thing you just have to look at is, do I have vertical rectangles or am I looking at horizontal rectangles? And so what you want to realize with this picture here is that there is a curve that is more on the right, and then there's a curve that's more on the left. And what I mean by that is that there is a curve that is always on the right hand side and always greater than the other one. So it's really what tells us that we want to focus on rectangles that sit this way in the horizontal. And we can see that y equals x minus 1, which does happen to be a function, is always on the right side. And it's very easy to then also write that as x equals y plus 1. It's very easy to interchange how it's written. The other curve here is not a function. It's a sideways parabola. And the important thing to see is it is always on the left. And so we can always find the height or length or however you want to call it of the rectangle. This distance here is always the curve on the right minus the curve on the left. So we can see that we're given the points of intersection. So those are going to be our limits of integration, and it's going to be from -2, so notice I'm using the y value because I'm going to be integrating here with respect to y. So I'm using the y value of -2 up to 4, like that. And then I'm taking the curve on the right, which is y plus 1, subtracting the curve on the left, which is 1/2 y squared minus 3, and then not forgetting to multiply by dy. So we want to find the area within this here. And this is the integral setup. So now all we have to do is integrate. And what I might do first is write this, you know, combine any like terms, distribute that negative. So I'll have a negative 1/2 y squared. I'll have plus y, and then I have a 1 minus a negative 3, so I'll have plus 4. So if you want, you're welcome to pause the video, see if you can find the antiderivative and evaluate it correctly. So it looks like we'll have y cubed, a negative 1/6 y cubed, plus 1/2 y squared plus 4y. And that's going to be from -2 to 4. And then it's just evaluating. So at this point, I'll have a negative 6, and then in my numerator here, I'll have 4 cubed, which is 64. So negative 64 over 6, plus I'll have 16. When I put in 4, 16 divided by 2 is 8, plus 4 times 4, 16, minus what happens when we put in a negative 2. So it looks like we'll have a positive 8 over 6, because I'm going to have a negative 8 times a negative 1/6, and then plus I have y squared, so I have 4 times a half, so 2, and then it looks like a negative 8 here. So let me just check my numbers. Yes, that is what I have. And so if we put that all into the calculator, what we're going to find is that we get 18 units squared. So we are finding area here. But our answer is still just a number. It's still the area in between. It's still positive. So all of that's the same. The key thing to understand is just everything needs to be written as x equals here in order for us to look at the rectangles as horizontal. Now this is a new one here in that we don't know. We see that both of them are solved for y, so we're thinking that we're going to be doing vertical rectangles, but we don't have a graph of it, and we, you know, that's not really helping us. So the first thing I might do is graph this, and so I'll consider, you know, I can just think of this as y1 here and y2. It's not necessary, but you could. So I'm going to do my square root function. So it's just square root of x, but it's shifted up 1. So that's something you should know. So when x is 0, y is 1. I'll pick some good points. So when x is 4, I get 3 here. And when x is 9, I get 4. Okay. So this function looks a bit like this. Okay, at least for, you know, what I have here. Then if I do 1/3 x plus 1, well, that also has the point 0, 1, so that's helpful. And then maybe I put in the point 3, because I'm going to multiply that by 1/3 to get 1, and then add 1 and get 2. You would also do it by the slope. Once you have a point, you can go up 1 over 3, up 1 over 3. And that's a line, so we do want to make sure that we show that it is a line to the best of our ability, of course. And we can see that here is our function. So it's going from 0, 1 to 9, 4. And that we're finding this area in here. And what we should see is that there is always a function here that is on top, that these are functions, and there's one function that's always on top. So in this case, I would make a focus of doing a vertical rectangle where I see that this function is always on top of this function. So the height is just the difference. Now, if you are not given a graph and you don't want to do a graph, then the best thing to do is find the intersection points, and that's common. And intersection points are just found by taking the two functions and setting them equal to one another. So we're going to have this. I can see pretty quickly that my 1's are going to simplify and be gone. And then I have a negative square root x equals 1/3 x. Oh, sorry, that's not a minus, that should be a plus. Even easier. So now we square both sides. So I'll have x equals 1/9 x squared. If I don't like the fraction, I could multiply through by 9 to get 9x equals x squared. And just for space saving, I'm going to move this up. So I'll have x squared minus 9x. And by factoring, I get x minus 9. And that tells me either x equals 0 or x equals 9. So those are the x values we got anyway for the intersection points. I'm just letting you know that that would be another way to do it besides graphing to see where the points intersect. I mean, we are not told from 0 to 9, so the only way to find that area is to find out what area is enclosed, and that's why the intersection points are necessary. But now it does allow us to write this as 0 to 9, our limits of integration in the x direction. And that function on top is 1 minus the square root of x, and the function underneath it is the line 1/3 x plus 1. And then we do have, in this case, a dx, like that. Okay, and so now we just evaluate. So as I typically do, really the best thing is to make your life easier to combine anything that you can. So the ones are going to be gone. We can see that. Why do I keep writing this as 1 minus? 1 plus square root of x. Okay, so now we can see that the ones are going to simplify. We'll have the square root of x, or x to the 1/2, minus 1/3 x. And that is still dx. I have not taken my antiderivative. Now I'll take my antiderivative, so we'll have x to the 3/2 times 2/3 minus, and then I have 1/6 x squared. So I'm adding 1 to that exponent, dividing by 2, and that is from 0 to 9. Now as I evaluate it, I will have 2/3, I have x to the 1/2, which is 3, and then 3 cubed is 27. And when I put 9 and square it, I get 81 times 1/6, so 81 over 6. And then we'll be subtracting from that what happens when we put in 0, but oh yay, it's just 0. So then that just leaves us with what we have there, and we can find that it should be 4.5 units squared.